I might do something different, which is talk about something that's a pretty new project for me, for a couple of reasons, one of which I thought it would be fun to talk about something new. But secondly, in the spirit of this seminar series, it's actually an all-female team. And so this is some work that I'm doing with my colleague, Alexis Sichler, who's a geochemist at Mines with me, and a postdoc, Beth Hoagland, who came to us as a biogeochemist, and Ariel Rickel, who's a master's student who did a bunch of the geophysical work. So I will say that has changed in my career, and that early on, I very rarely worked in all-female teams, but that has changed a bit in recent years, which is interesting. So I thought I might start with background because that's what the last two speakers did, and I thought it was quite interesting to hear where people came from. So let me try to go forward here. So I'm going to start way back, which is, these are my folks. So my mom here is on the right-hand side. She was a first-generation college student. She grew up on a farm in Appalachia, in a pretty poor area of Ohio, and here in the United States. And she got to go to college because she was named after an aunt who had never gotten married, never had kids. And so when she passed away, she left money for my mom to go to college rather than her three brothers. And my mom will say that this fundamentally changed everything for her, that she was able to sort of see what was out there in the world, even though her only choices for majors when she went to college were nursing, teaching, and something like home economics. This photo on the left-hand side is my dad, and the little fat thing he's holding is me. My dad came from a very different background. He came from a very wealthy, well-connected family in India, and he came to the United States for his PhD and met my mom during that time. So I guess the short version of my upbringing was that education was incredibly important to my parents for different reasons. But my brother and I grew up in a household where it was pretty clear that going to college was something we would probably do. Despite that, I did not have any thoughts that I would be a scientist. In fact, I was the editor of my high school literary magazine. I thought I would write poetry, even though I found some old photos that might indicate some differences of, you might have seen my STEM feature here, some early experiments in hydrology, where apparently I had already learned that dressing like a man might get me somewhere. Here, I think this might be high school, and you can see the 5 1/4 drive here. So I was probably dealing with many bytes of data, so on my way to high performance computing. But it was probably college before I found my path. I sort of fell into the world of geophysics. Probably like many of you, I had a great teacher in high school who was a physics teacher that made me realize how cool physics was. And it was through that and my desire to do something that helped the planet that I sort of fell into geophysics. This is an old photo from my undergrad years using a ground penetrating radar, which is an instrument I am truly bad at, but it was really fun for me to be able to use these methods to understand things about the subsurface. I was super excited because I found this video from the 90s from my undergraduate thesis. It is very not exciting, but the work was basically, I had a block of granite that has a fracture in it. So what you're looking at here is a ground penetrating radar record. Here is just the surface of the granite, the air wave. But here's my fracture, and the entirety of my undergraduate thesis was that this fracture was filled with water, and then I displaced that water with gasoline while imaging this with ground penetrating radar, and then the fracture disappears because the dielectric permittivity contrast between water and granite is quite high, and it's quite low between gasoline and granite, so you can't see it anymore. That was basically my undergraduate thesis. It's really not exciting. Sadly, the movie won't play anymore because the 90s codecs or whatever are out of date, but I was really excited to show it to you, but I can't. But this did set me on the path for where I am now in my career, which is someone who uses geophysics in part to understand what's happening in the subsurface. I like to think about geophysics as being a sort of a macroscope. We all know what a microscope is, right? But it's a sort of a way to look into the subsurface and see big picture features in a way that we might not be able to see. I think of these tools as minimally a better way to interpolate between the boreholes and the soil pits and things that we have, but maybe better is a way to be able to explore subsurface properties and processes on a scale that we might not otherwise be able to see. What I'm showing you here are two examples from actually both from the Boulder Creek Critical Zone Observatory. It's a really nice work of Kevin Beefus, who I think is actually online, from his master's thesis, showing the difference in seismic velocity across across these hill slopes. And what you see in his work is that you see more broken up rock, you see lower velocities at the near surface on his north facing slopes and on the south facing slopes. Some work from St. Clair et al. That I was lucky enough to be a part of is in a different part of that system, but actually shows something slightly different, which is that we don't see differences in that seismic velocity across slope aspect. And so what's neat about this is it opens some questions about why things look different within the system. Is weathering related to stress, or is it related to freeze thaw processes? Only through having these data can we start to see the landscape over larger scales. Now, for me personally, what makes geophysics so interesting is being able to get it processed. And so here's some old data from some work I did with John Nimmo at the US Geological Survey many years ago, where we were trying to image the migration of water, infiltration of water into the subsurface. So we have a small infiltration ring on these soils, and there's two different sites here, one in the left column, one in the right. And what you see in the left-hand column in the sort of sandy soils is that what happens in the infiltration ring, which is sort of right here in the center, a meter in diameter, is that the water sort of moves in like plug flow, which are the assumptions we often make about infiltration in the subsurface. But in the soil over here that had undergone more complete, more advanced pedogenesis, where things were more complex, it really doesn't look like that 1D plug flow. So what I think is really cool about these methods, both this data shown here and the ones on the last slide, is I think they help us develop hypotheses about what might be happening in the subsurface and allow us to sort of question our understanding of a system in a way that we might not be able to do otherwise. So I got my PhD in hydrogeology, and so that sort of is how I've ended up where I am. And one of the things I started thinking about not long after my PhD was the role of sort of dead end or less mobile, immobile pore space in aquifers. Now, why this matters is because when we have issues with contamination, when it ends up in the subsurface, it will migrate really quickly through the highly connected, the highly permeable path. But where things get tricky is that that material will also diffuse really slowly, in this case, into the matrix or into the less mobile dead end pore space. It might stay there for a long time. And so from a contaminant transport perspective, this is why we see sort of, sometimes they're called secondary sources, material that will leach out over decades. And so at long times, it may be that the highly permeable pathways clean up, but we still have contaminants or solutes, whatever we're interested in, sort of trapped in the less mobile porosity. Now, this idea isn't new. There's an image here from Coates and Smith from 1964 from a Society of Petroleum Engineers manuscript that shows the same idea, that we've got these well-connected pores and then these less well-connected pores. They're calling them here stagnant volumes. But what this means to us as hydrologists is that when we think about concentration histories, so concentration through time plots, if the system was just described by advection and dispersion and diffusion, so the advection dispersion equation that many of us use, you'd see something that is almost Gaussian in time, Gaussian in space. But because of this idea of dead end pore space, what we end up seeing are concentration histories that are much more complex. We see these really long tails out the backside, meaning higher concentrations than might be expected from that advection dispersion equation. We sometimes see double humps and some other interesting things. So as part of my early work, I really got interested in the idea of using geophysics, coupling that with electrically conductive tracers like sodium chloride to be able to get at that immobile pore space. The method I'm going to talk about most today is electrical resistivity, which is still my favorite of the geophysical tools, in part because I think it's reasonably straightforward to use and tells us a lot of things that hydrogeologists or critical zone scientists might be interested in. These methods are sensitive to the lithology of the subsurface, the porosity, how connected those pores are, their salinity, and it's also sensitive to things like moisture and temperature, which can both be an advantage and a hassle depending on what you're looking for. The way the method works is, for those of you that are hydrologists, I saw there were a fair number here, it's almost like a two-well pumping test where you would be injecting water into one well and pulling it out of another. We're just doing this with current. And then we measure the resultant change in potential. In this case, we're talking about voltages rather than heads from two other locations. And from those data, we can reconstruct maps of the subsurface electrical conductivity. And if we think about those data in a time-lapse sense, like I was talking about with those soils a second ago, and we're using conductive tracers, if we measure the temperature and the moisture and can constrain those things, then we can really use these data to focus on changes in salinity and look over a much broader swath of land than we might be able to do from the point scale measurements that we typically have. Now, when we use these conductive tracers in geophysics, one of the things that we've seen in aquifer systems is that there's a hysteresis between the apparent bulk conductivity, what we're measuring from the geophysics, and the fluid conductivity that, say, we might measure from a piezometer. Now, the relationship that we use often in geophysics to describe the relationship between bulk conductivity and fluid conductivity is Archie's law. It's a straight line relationship between the two. Now, what's interesting here is we don't see that straight line relationship. And all hysteresis says is that whatever's happening on the y-axis is not happening at the same time as what's happening on the x-axis. And we think this hysteresis is probably happening because what we see with the geophysics is sensitive to both the connected and the disconnected pores. Whereas what we measure in the fluid conductivity, what we see in our piezometers, is just a function of what's connected, what's mobile. And so that difference in timing between how things move, just like in that contaminant example we were seeing in the fast flow paths versus the slow flow paths, leads to this hysteresis. Now, of course, I realize this is a talk supposed to be on rivers, so I'm going to move us there, but all of this is going to come back to play as I start to talk about some of the data that we are getting from these surface water, groundwater systems. So for many people here online, I know think about these systems as well. We know that the connections between groundwater and surface water are important for a lot of reasons. One of the things it does is it increases the residence time of that surface water, and that allows for the sort of biogeochemical hotspot that's at that surface water groundwater interface to do geochemical work, things like metal uptake or nutrient processing. It also provides thermal buffering for, say, fish refugia. So lots of people have been working on this idea of the hyporeic zone, hyporeic here from two Greek roots, hypos meaning below and rios meaning flow, but it just really is the part of the aquifer system where surface water becomes groundwater, becomes surface water again. So I ended up working in these systems because of my interest in dead end pore space. And what happened was I sort of got pulled to the surface as a function of Mike Gusev, whose image is shown here, who was a good colleague of mine at Penn State. He's now just up the street, actually, at CU Boulder. So we still get to work together, which is great for both of us, I hope, well, at least for me. And so one of the things when he interviewed, he showed the same equations that I use to think about dead end pore space in aquifers to describe what we call transient storage in stream systems, stuff getting stuck. And he showed those same equations. I remember walking up to him and thinking like, but hey, those are my equations. And in that process, we started to think about how we might be able to work together. So we wrote a proposal that got funded, and I'm showing you an image from this proposal from a while ago, that we really wanted to understand something about the size of that hyporeic zone, that size of the area where work can be done, and how big it was, how spatially and seasonally consistent that zone was, how was it controlled by, say, changes in discharge through the year, and could we map that sort of immobile part of the stream system using geophysics. Now, the hypothesis we put forward, which I'll come back to in a second, was that, well, maybe in spring months, at least here in the Northern Hemisphere, when water tables are high, what that would do is that pressure would sort of act on my stream, would squish my stream such that my hyporeic zone would be small. And then in summer months, when the water table relaxes, when there's sort of less base flow or groundwater contributions into my stream, maybe my hyporeic zone would be larger. So that is what we put forward. Now, in terms of being able to map how big the hyporeic zone, you have a couple of options. So traditionally, the way we did this is aquifer acupuncture, right? So we put a bunch of holes in the ground and we try to map where our tracers go. The other option is for you and your friends to get together and get a big trash can full of dye or full of salt, and you drop it in the stream and see what happens down gradient. Now, this will be familiar to you, but in a stream system, if we only think about advection and diffusion, we see a concentration history or a concentration breakthrough curve that is almost Gaussian, has a little bit of a tail here in time, exactly like we see in aquifers. But what we see in many of these systems is a long tail, just like we see in aquifers. But instead of being just dead end pore space, here what we're talking about is stuff getting stuck in eddies and in the hyporeic zone of a stream. But we see that same behavior of these long tails to time. And that's why the mathematics looks so similar to what we do in aquifer systems. So as part of this project, we used electrical resistivity in conjunction with the tracer test to try to map that hyporeic zone. So I'm going to show you is that work. This is a really nice work of the PhD of Adam Ward, who was working with us at that time. And so I'm showing you here some cross sections of a pretty small stream. This is actually from the H.J. Andrews in Oregon in the Western US, for those of you who may be familiar. You're only looking down a few meters here, 4 meters and sort of across sort of 14 meters. So it's a small stream. What I'm showing you in these 3 different time slices is the river at different discharge. So 33, 7, and 4 liters per second. The yellow sort of contour here is basically the size of the stream in each of these three cases, so you know. So what we're doing is we're 3 hours in here, and this is a cross section where the water is, say, coming toward you. 3 hours into a sodium chloride tracer tress. It's been mixing from upstream, and now it's coming through, and we're mapping it with the geophysical data. Now, 6 hours in, 12, 24, 48 hours in, we injected this tracer for 48 hours. What you see in part is not surprising, which is that the stream itself becomes really electrically conductive. We put a bunch of salt in a stream that goes without saying. But what's cool about these data is what you can see around the stream, which is this sort of halo around the stream itself. And so what we're seeing here is that hypereic zone. We're seeing where that salt has sort of migrated out of the stream, which is where it was injected, into the aquifer around it. And what's really cool is that we kept imaging after the tracer passed by, and it's most obvious here at the highest discharge case that the stream goes back to background conditions pretty quickly, and we see this bathtub rain of salt where that material is still in our aquifer system. And if we come back 24 hours later, most of that salt is gone, but we can sort of see where that salt has gone. Now, I would be hesitant to estimate areas from these data, and we can talk more about that later, but there's a lot of assumptions that go into reconstructing geophysical images, and these are two-dimensional slices of a three-dimensional system. But despite that, what we can still say is that we can generally see where tracer is going, and we can see how it changes between these 3 times a year. Enough to say that this hypothesis is just flat wrong, right? And part of the reason that this hypothesis was incorrect is that we really came at it, and I must have like won this battle, but as a groundwater hydrologist, right? I was thinking about what the water table was doing to the stream, but I missed something fundamental in what we drew here, which is that the size of the stream is different too. And so its pushback on the groundwater system is different than what we sort of anticipated when we drew those arrows. So I guess what I'd like to say is that, we've done a lot of work through the years. A lot of people have done a lot of work on hypereic transport, surface water, groundwater interaction at a variety of scales. This is a super nice image from Biani Cardenas, sort of drawing all the different pathways in which we see surface water, groundwater exchange. But most of this work, I would say a lot of it at least has been physical, probably because for many of us, our training has been more physically based. And yet the proposals, at least that I write, are often motivated by the biogeochemistry. Why do we care about the hypereic zone? Is because of the biogeochemical work that can be done. So the project that I'm going to start talking about now was exciting for me to be able to do that in working with Alexis and Beth and Ariel. So one of the things we wanted to look at were, say, CQ, concentration discharge relationships. And these have been reasonably commonly used within the hydrologic sciences. What we do is we plot the discharge of our stream in log space, the discharge of a concentration of some constituent in log space, and then we calculate a power loss slope B. And this power loss slope will come back a few times in this talk. But so what you can do from those slopes is start to talk about process in terms of what's happening within the stream. So for instance, if we look here, this is a nice paper by Motar et al., where they looked at almost 300 different stations in France. You see, for instance, the dissolved organic carbon is what we would call chemostatic. No big changes in that chemistry with discharge. As discharge goes up, the concentration stays the same. Meanwhile, if we look at things like chloride here, we see what we would describe as a dilution signal. As we increase the discharge, the concentration goes down, so that additional water dilutes the concentration that we're seeing. Up here in total suspended solids, we see the opposite, which is a mobilization type behavior, which is as the discharge goes up, so does the concentration. And so from this, we can start to answer some really interesting questions about what are the sources of stream water under sort of differing flow conditions, and also what processes matter, both in terms of the solute transport, but also solute generation and biogeochemistry. Now, note there's some other relationships here I haven't mentioned that are more complex. Certainly feel free to check out the Motar paper. They were looking at some biological activity as well. But one of the things Beth was really interested in when she came to mind was thinking about these sorts of relationships and the role of the hypereic zone with respect to trace metal export, just because there had been a bit less work on that. So I pointed out that this was sort of a critical zone talk, so I guess I should probably briefly talk about critical zone stuff. And this idea of critical zone science, right, is just thinking about integrated earth and environmental science. And we might think about that over this block of material that goes from sort of atmospheric boundary layer to the base of groundwater. But in this case, what Beth's work really looks at in terms of surface water, groundwater is still tied to these critical zone themes. Pam Sullivan put out a nice white paper a few years back that highlights a bunch of sort of open questions within critical zone science that might be of interest to some of you. But some of the things that were specific to groundwater surface water exchange were in this new opportunities was the idea of being able to define what is a transporter system versus a transformer system. How does the geochemistry change within a system, and how does the connectivity of, say, surface water and groundwater, or even parts of the groundwater system, control what's transforming versus transporting. Other open questions within this document talk about structural controls. So how does the shape of the critical zone change hydrologic functioning and consequently the biogeochemistry of that system? And then other things that are related to this work too, the distribution of microorganisms, which we'll talk about really briefly. And then what are the controls on these concentration discharge relationships that we were just talking about? So I'm going to take you to our field site here in southwestern part of Colorado. This is the Animas River watershed, and we're going to work in a couple of small headwater streams, Cement Creek and Mineral Creek. Now, a few of you may have heard about this area because of the Gold King mine spill, which was sort of a big deal in 2015. What I'm showing you here is the video on the right was made by the EPA in response to an accident that happened in 2015. So a US EPA contractor disturbed a plug to a mine adit while doing just sort of a routine investigation, and that dumped 11 million liters of acid mine contaminated waters into the upper Animas, and this moved downstream. And so this video that you hear on seeing on the right shows this spill, which happened into a creek known as Cement Creek, which we'll talk more about in a minute, which is a headwater of the Animas River, which is in turn a tributary to the San Juan River. And this video is about 10 days long, so 10 days from the blowout, and is looking at 200 kilometers downstream. Now, there's a lot of interesting things about this spill. Certainly, there's an environmental justice aspect to this too, because all of these gray lands here are part of the Navajo Nation. It turned part of the Animas bright orange for a period of time, which is certainly exciting. And while this is a big deal, this 11 million liters of acid mine drainage, I should point out that about 20 million liters of acid mine drainage is thought to contribute to these rivers via diffuse sources. So it's a big deal, but is within sort of, I shouldn't say it's within the noise, but I mean, there's a lot of contaminated, metals contaminated streams and rivers in this particular area. So one of the questions we wanted to ask is, what's the role of surface water, groundwater connectivity in sort of mediating that toxicity and that mobility and thus metal fluxes? So if we zoom in to the sites that we're working on, here again is Colorado. We're in that same part of the system up in the upper Animas. We're going to work in 2 watersheds, including Cement Creek, which is where the accident had happened, and then another parallel stream system. We'll talk about their similarities here in Mineral Creek. All of these black dots, though, just to highlight over here in the map of the state of Colorado, are old mines. So we very much live in old mining districts here. So there are a lot of acid mine impacted streams, both from mining and just sort of natural release of metals from these systems. So some of the questions that Beth wanted to look at as part of her postdoc was, what are the controls on hyporheic zones on this acid mine drainage? And how does the hyporheic zone mediate that metalloid transport? And if it does, like, when, how, where. This is an image of Mineral Creek here in Silverton, Colorado. This is Ariel, I believe, in the field. And then here's Beth on a bit of an iron fen, which we'll talk about in a little bit. So the 2 systems are shown here, Cement Creek and Mineral Creek. We treated them fairly similarly in that we did some tracer injections up here at the blue dot in both of them. I guess it's actually a blue diamond, sorry. And then downstream from that, we took in-stream samples. We put in some electrical conductivity loggers. We have a series of boreholes, both within the hyporheic zone and some stilling wells and a groundwater well for some indication of what's within the groundwater. We'll talk just a little bit about some electrical resistivity. I'm going to just focus on the Cement Creek site for that. But what makes these sites particularly interesting is that Cement Creek has a ferrocrete layer in it. So what this is a conglomerate that's cemented together by iron oxyhydroxides, and it's about 40 centimeters deep in that stream. And you see this layer at that depth. And to form ferrocrete, and the word crete here is just like concrete, like celastic, I can't even say that word right now, like silicretes, I guess. In this case, you need oxygenated stream water and low oxic groundwater to mix to lead to the precipitation of these iron oxyhydroxides. And then the ferrocrete eventually will shut off that mixing because its permeability is so low. So some of the questions we had is, do we need strong upwelling of reducing groundwater to form that kind of system? Now, we don't see that in Mineral Creek. When we look in the Mineral Creek stream bed, it just looks like a normal stream bed that you might see somewhere else. So what we did is we did a couple of tracer tests at sort of high flow right after snow melt, which happens quite late in this area because we're at pretty high elevation. So we have a tracer test that we conducted right at the end of July or beginning of August, and then the stream drops discharge pretty quickly. And so we did another tracer test at sort of lower flow in September. Now, what I want to compare for you, or to make contrasts between these two sites, is that they're fairly similar in terms of the size of the stream and their stream flow, both within the high flow and the low flow period. Cement Creek and Mineral Creek look pretty similar to one another. Where things are different are partially in their chemistry. So the pH of Cement Creek is quite a bit lower than that of Mineral Creek. The electrical conductivity, so as a proxy for total dissolved solids within that stream, is also much higher in Cement Creek than Mineral Creek. The other thing we did is tried to measure the stream bed conductivity through some slug tests, and take it for what it is. A slug test is only so accurate, but the stream bed conductivity is a bit lower, not surprisingly, in the Ferrocrete than what we're seeing in the gravel bed here of Mineral Creek. Over these times, we also know there's a bit of a changing hydraulic gradient between the sort of high flow and the low flow scenario. It's a little hard to see because we only have a limited number of piezometers. So this is not exactly to scale because I'm showing the stream as being the same height in both high flow and low flow. So take that for what it is. But over here, I'm showing you Cement Creek, again, the one with the Ferrocrete in it. Cement, named Cement Creek for a reason. That Ferrocrete layer is shown here at about 40 centimeters depth. We have a series of piezometers above, below, and sort of in the Ferrocrete. At high discharge, we're seeing downward flow, although we're not sure how much flow is getting across this Ferrocrete layer. At low flow, we're seeing slight upward flow. In Mineral Creek, at low flow, we also see slight upward flow. It's pretty hard to tell from the data we have what's happening at high flow. It's just mixed because of the heterogeneity that's in the field. So what we did is these couple of tracer tests, which I'll show you here. So this is Cement Creek, again, so our cemented stream. And I'm showing you the two tracer tests, one here at high flow and one here at low flow. And the model here that we're using to fit our data, which are shown as black dots, is Otis, the one-dimensional transport with inflow and storage model. So what you can see in this particular data set is that alpha here describes the rate at which solutes can move from my stream to my hypereoic zone, so back and forth between those two. And then this A sub S divided by A value here is the area of the hypereoic zone, or the area of the storage zones with respect to the area of the stream itself. And so the thing to notice with these data is that we don't see big differences in the exchange rate, so how fast things are moving between the stream and the hypereoic zone, but we do see a slightly smaller hypereoic area at low stream discharge. And that fits, for instance, with the data that from Adam Ward's thesis from Oregon, for example. People have seen the opposite in other systems, but we see something similar here. Now, if we compare those numbers to Mineral Creek, which does not have that Ferrocrete layer, what you see is that in general, exchange rates are a bit higher in Cement Creek, so things are moving back and forth a bit more freely. But more importantly, perhaps, is that the area of the hypereoic zone is sort of 3 to 4 times larger in Mineral Creek than it is in Cement Creek. So there's just more area for that sort of biogeochemical work to be done. Now, what Ariel did for part of her master's was to try to image this with some geophysical data. And so I'm going to just show you some of her images for what it's worth. And so she wanted to see, could we actually see differences in hypereoic exchange between these two time series. So here are a series of electrodes going across Cement Creek. You can see the sort of very orangey color of that stream. So here are her background images from Cement Creek. So you're looking at a cross section. Sorry, this is about 25 meters across. The axis here seems to be missing. You're looking about 5 meters down. So we've got our stream. Shown here, there's this iron fen that's fairly conductive on the one bank. And what we did is we introduced the tracer just like we did in Adam Ward's work, and we migrate it through the system. Now, probably the most notable thing you could hear, there's a fair bit of noisy stuff that sometimes happens with inversion, but the thing that is most noticeable is that you see this sort of solute sticking around in the hypereoic zone a bit longer at high flow, which would imply that we have a higher residence time at high flow than we do at low flow. And we thought we would take a look at that and compare that to some of the data that we got from the solute tracer tests. But what Ariel did for part of her work was took a look at that idea of those hysteresis plots that we talked about back at the beginning of this talk. And so she plotted both her in-stream electrical conductivity and then sort of an average of her bulk electrical conductivity, which apparent conductivity, which I'm happy to talk more about, to plot these hysteresis curves. And one of the things that she saw was that at low flow in Cement Creek, those two things start to collapse to that straight line, like would be predicted by Archie's law. And that would imply that what's happening on her x-axis and her y-axis are changing together, that our fluid and our bulk don't seem to have that offset in timing. And this would work if we're primarily sensitive to what's happening within the stream and don't see a lot of exchange into the banks. Of course, at high flow, she sees something different, which is a much larger hysteresis curve, implying again that we see more exchange between the stream and the aquifer surrounding it at high flow, which fits with the tracer test data as well. Now, what we wanted to do was take a look at what this means for the biogeochemistry. So I'm going to compare some of these results now to some of the nice geochemical sampling that Beth did. So here are these two creeks. There's a lot going on in this plot, so let me try to walk us through it. So here's Cement Creek on the left-hand side. You see that ferrocrete layer again here at about 40 centimeters shown in red. Over here is Mineral Creek, so that's our one that is not cemented. You are looking at data from different discharges, so from sort of a lower to a higher discharge. You're also seeing in the solid lines what we measured as the total concentration. What's happening in the dotted lines is what we're seeing as the dissolved concentration, or what passed through a 0.2 micron filter. The first thing I'll point out in Cement Creek and Mineral Creek is sort of an estimated hypereoic depth based on that Otis modeling. So here in white is showing you the approximate depth of the hypereoic zone that we are attributing to these models. You can see that it's quite shallow in Cement Creek at low flow, and it's a bit higher down to the ferrocrete at higher flow. In Cement Creek, we see a much bigger hypereoic area, hypereoic depth. We see here in low flow, it goes all the way down to sort of 60-ish centimeters. And at high flow, I actually cut off the bottom of the image. It goes down to about 1.2 meters. A couple things that are noticeable about this plot. One of which is that I've highlighted a few of the axes here to point out that they're not the same. It was actually hard to plot these data in a way that allowed you to see what was happening in both systems while keeping the concentration axes the same. And that's because there's just higher concentrations of some of these metalloids, specifically aluminum, magnesium, and iron within Cement Creek than in Mineral Creek. One of the other things we see in Cement Creek is that this low permeability layer seems to partition these metals and as well, and sulfate as well in Cement Creek. And we don't see those changes as much in Mineral Creek. While we do see a big kick in concentration at our lowest sampling point in Mineral Creek for some of these materials, keep in mind that the axes here are really extended rather than going from 0 to 1200 micromoles per liter. Here we're looking at 0 to 150. The other thing about this plot is, at least for me, it's pretty hard to parse the changes in concentration with discharge from this plot alone, in terms of that, or even the differences between dissolved and total constituents. So what we're going to do is we're going to take these data and put them onto sort of those CQ type plots that we were talking about before. Now, the struggle that we had in doing that was that if you just use that power law slope B by itself, it actually can be a little bit complicated to interpret, say, chemostatic behavior when that concentration isn't changing with discharge. And that's because variability in concentration could be high as just a function of the discharge itself. So the slope itself might be small. So what we decided to do was plot that power law slope against the coefficient of variation, the ratio of concentration to discharge. And that way we could sort of address that issue of big variability in C by normalizing it by variability in discharge. And that allows us to figure out where the sort of mobilization patterns are and the dilution patterns that we were talking about earlier. And then we defined our chemostatic zone here is things where that power law slope was low, so plus or minus 0.1, and also had a low ratio of these coefficients of variation between concentration and discharge. So I'm going to show you a plot that looks just like this on the next slide that shows you our data planted on top of that. Okay, so here is that plot. Here's the power law slope. Here is that ratio in the coefficients of variation. Now, there's a few things, I guess, to note on this plot. One of which is that Cement Creek is shown in red and orange. So the data tend to cluster sort of down here. And again, the darker color is total, the lighter color is dissolved. And so you're seeing that Cement Creek is sort of down here and that Mineral Creek is sort of up here. So what that means is that in general, we're seeing more mobilization behavior in Mineral Creek and a bit more of that dilution type behavior in Cement Creek. The other thing that is interesting in these data, if you spend some more time, I should point out, Beth did publish this paper in December of last year, so it is available in Frontiers in Water because there's kind of a lot in these plots. But the difference in that power law slope for the unfiltered samples, so the total concentrations versus that dissolved sample, what went through the 0.2 micron filter, is a lot different. It's a lot smaller in Cement Creek than it is in Mineral Creek, at least for aluminum, iron, and copper, and magnesium as well. And so what we thought that might mean is that more of these metals are being transported as colloids or attached to particles in Cement Creek than Mineral. And we tried to show that down here. Here again is the power law slope. And here's that concentration ratio of dissolved versus total constituents. And what you can see is that in Mineral Creek, you see sort of a broad distribution here, where when we get to Cement Creek, more of those ratios sort of tend toward 1. So from that, we tried to build some conceptual models of this system. One of the things that we thought about is that how does this low permeability layer impact what's happening? Well, certainly by having a ferrocrete layer there, you have a smaller hypereic area. We see that in our tracer test data as estimated with Otis. We see less exchange potentially from the geochemical data. We're seeing these negative power loss slopes. So we're seeing more of a dilution trend. And that would imply that the sort of hill slope flow contributions are maybe a bigger deal than in-stream processes for this particular system at least. When we look at Mineral Creek, we don't have that ferrocrete layer that's sort of bounding the hypereic zone. So we see a larger hypereic area on the whole, and we see more exchange, again, based on the tracer data that we have. And so what we're seeing is a mixing of some metal-rich groundwater within the system and this oxygen-rich stream water that is leading potentially to the precipitation of metal oxides in the subsurface. And that might define why we have these power loss slopes. Now, the other thing that Beth is looking at and still sort of working at in this data is how this hydrologic connectivity may influence the microbial community composition. So this is obviously, I'm a physical hydrologist, so talking about biology makes me slightly uncomfortable, but we'll give it a go. What I'm showing you here is an alpha diversity measure. Shannon diversity is simply a measure of species richness. So what we're seeing, there's not enough sort of groundwater data to say much about. We just have a couple of samples from Cement Creek. In Mineral Creek, if we look, or in both creeks, if we look at the sediment, things are pretty mixed up. But in terms of where things look quite different is within the pore waters themselves between Cement Creek and Mineral Creek up here. Now, in Mineral Creek is, as we know, is sort of oxygenated. It's a metal poor stream. The stream water is mixing with these metal-rich groundwaters, and what we're seeing is species richness is high in that particular system. So there's questions about whether this could potentially enhance natural attenuation of these metal-impacted streams. Now, Cement Creek, shown in red, has that poor surface water groundwater exchange in part because of the ferrocrete, and that might facilitate some redox stratification or maybe some niche microbiome assembly. So that is still sort of working on some of the biogeochemical data for the system. So on the whole, there's some implications for remediation here, right? That disconnected systems like these ones shown here with the ferrocrete layer might benefit from some subsurface reactive barriers or removal and treatment of sediments. It's just hard because there isn't, a hypereic zone can't do the sort of biogeochemical work it can when you have a much larger area in which to do that work. So remediation efforts in systems like Mineral Creek could focus more on that stream water treatment. And so I think one of the things that was exciting for me in this project was being able to sort of think across these disciplinary boundaries. Someone like me who's a physical hydrologist and geophysicist, getting to sort of think about these systems within the context of biogeochemistry, at least for me, was pretty exciting. So while I have the floor, I will make a shameless pitch. There's a research coordination network that I'm currently the PI of. It's funded by the US National Science Foundation. That's trying to attract new scientists to critical zone science. So if anyone out there is an early career researcher that has an interest in sort of integrated earth and environmental science, we're trying to provide seminars that are super accessible for people that are outside sort of these integrated disciplinary areas, some career development programs, et cetera. You can check out our website. This is also the website if you're sitting there with your phone right now. We're also on Twitter at Join CZ Science. And so we're trying to engage the next generation in some of the interesting and important questions that are out there in these integrated systems. And so with that, I will close this out. I want to thank you all for your time. This is me if you'd like to contact me after the talk, and I appreciate you taking the time to hang out with me. So with that, I'm happy to take questions.
Thank you, Kamini. That was a really interesting seminar. And if you haven't attended these before, what we would ask is that you submit questions through the chat, and then Lily will read those to Kamini and should be able to answer them. While we're waiting for the questions to come in, I will just do my own quick advertisement. The next seminar in this series is on May 18th. Michelle Kappas, and I apologize if I'm mispronouncing her last name, is going to be giving us, I think, a very non-traditional approach to looking at braided rivers. So we hope you'll be able to join us for that as well. But let's see if we've got some. Well, there's complimentary things coming in, but no questions so far.
And lies. I am clearly not a GPR expert. So.
Okay, we've got questions. Thank you. Please keep submitting them.
Okay, we have one first question. Will the hyperreal zone be the same size on a regulated and unregulated river?
That's an interesting question. So I suppose if we think about that area and we think about it being discharge driven, right? Differences in flow would potentially affect the size of that stream. One of the things I guess that maybe would come, like this might not answer your question, but it's where my brain first goes, is that when we think about regulated rivers, we're probably also thinking about sort of larger systems than a lot of the ones that I work in. So I work in a lot of headwater streams because that area of the hyperreic zone is really big in a headwater stream with respect to the size of the stream. So in terms of doing work, when we think about metal uptake and nutrient processing, that hyperreic zone has to be significant with respect to the size of the stream to be having much of an impact. So for instance, in the Mississippi River here, it's this giant river. And so that hyperreic zone is just this little tiny skin with that giant river. And so its ability to do work, although there's some work by Jesus Gomez-Velez and others that have shown some differences with this, but in general, its ability to do a lot of work is small because the hyperreic zone is small. And so the idea of a regulated river is interesting. I guess, for me, they would be bigger in general. And so the impact of the hyperreic zone might be small in both cases. In terms of that variability in its size, it might be less, right? Because the discharge is being sort of regulated through time. And so whether that has important impacts for the biogeochemistry of that stream might depend on the system, but certainly take a look at some of the work of Jesus Gomez-Velez, who has done some work on big river hyperreic systems with Judd Harvey, I think, and that might at least answer the questions about the implication of big stream hyperreic impacts.
Cool, thank you, Kamini. Let's see. Another question coming up is, are you familiar with any hyperreal exchange studies in incised and or prairie streams?
Ooh, prairie streams. Off the top of my head, well, we've done a little bit of work out in Iowa in some agricultural systems, although that's not the same thing. The person whose work I might look at for that would be maybe Pam Sullivan. She's been doing a lot of work out at the Kanza Prairie in Kansas. And I would think that they might have done some hyperreic work on some of the systems there. Off the top of my head, I can't think of a prairie system, but I'm sure there is work. And in fact, I know there's some hyperreic people on the call here. If anyone else can help with that question and knows of a system right off the top of your head, please put it in chat to help out. But I would take a look at maybe some of Pam Sullivan's work on prairie systems. That would be the first person I would think of at least.
What about incised streams?
Oh, some of our streams are incised actually. So we have worked in some incised streams. the work, for instance, Adam Ward's PhD work was mostly in incised streams within Oregon. We actually intended originally to do a comparison with that project between sort of the high gradient incised streams within Oregon and these low gradient, less incised streams within Pennsylvania. But it turned out that the Pennsylvania streams were really clayey, so we basically saw no exchange. But Adam Ward's work did have some incised streams, so that might be one place at least to start with that.
Cool. How might hyperreal dynamics differ in bedrock bound channels?
Yeah, so it turns out there isn't any in a lot of them, right? So we see that, for instance, some of our work in Oregon was between, I'm gonna forget now, watersheds 1 and 3, and one of them is bedrock confined, and one of them has much more alluvial, colluvial material. And what we see within those bedrock confined streams is basically no exchange over the time period over which the tracer tests are happening. The stream water is just way too fast for the exchange to happen with those bedrock systems. But in these colluvial materials, we see much bigger, or alluvial materials, much bigger hyperrheic zones. So yeah, so in bedrock streams, we don't. It's almost like coming back to being like a cemented canal, right? We just don't see a lot of exchange between the stream and the area around it.
Okay. Let's see.
There's a lot of questions now, Kamini. You're going to be here the rest of the day.
Here forever.
Yeah.
See what I can do.
A related question is, what might a hyperreal zone look like surrounding a karst conduit?
Oh gosh, it's like the world's hardest question. So karst and fractured rock are like the two things that like eat at my soul because they're so hard, right? Those two systems are so difficult because stuff can just shoot out. Now, I guess in a karst system, I mean, there's some interesting questions around to be hyperrheic, to be truly hyperrheic, it has to leave the surface water, go into groundwater and come back, right? And so in some of these systems where we have such high heterogeneity, we can just lose flow paths. And so they're not really hyperrheic, they're just losing streams, right? They're just losing flow paths out of the system. So I can imagine all kinds of crazy shapes that we might see in heterogeneity like that. But in terms of something being hyperrheic, you would need to be able to get it back into the stream. So, we have seen, this is not an answer to your question, but we have seen in some stream systems where we've done tracer tests using geophysics, we've been able to see the tracer in and around the stream itself, and also to occupy an old stream bed. So like, our stream is over here, and then there's like an old stream bed over here, and the tracer goes through here, makes the little bathtub ring we were talking about, and then it lights up way over here, completely disconnected. So I could see something similar happening within, say, karst regions where things are connected really interestingly, where, that tracer is going to take, water is going to take the most permeable path. So you might be able to light up things in some really interesting ways within karst environments that you might be able to see with geophysics. Fractured rock, the fractures are sometimes so small that with electrical imaging, the resolution might not be high enough for you to necessarily tell that something's a fracture. There'll just be a blob over there somewhere. But you might get some really interesting things in the karst environment.
Okay, the next question is about equations from Jan Seibert.
Okay.
You mentioned that your and Mike's equation were similar. Now you have been working more with hyperreal zone. What would you say is the same? Are they still the same or different?
Yeah, they're kind of still the same. So if I look at those equations, both of them look like an advection, dispersion, diffusion equation with an additional term. Now, okay, so I should maybe I'll answer this two ways. One of which is within the stream community, there is some consensus on, at least it seems to me, on maybe what these equations could look like in terms of transient storage. Certainly, we need to have in both aquifer systems and groundwater systems, we need a parameter that allows us to store stuff. That would be storage area. So that's eddies and hyperrheic area in stream flow. That's immobile pore space in aquifers, and we need an exchange rate. It seems like there's less, the word bickering sounds a little mean, but there's less bickering within the stream community around those equations than in the groundwater community. There is a lot of people in the groundwater community working on other equations that could be used to describe solute transport, from fractional derivatives to, there's just a whole variety of non-local models that are out there. And so it does seem like, from my perspective, what's hard about these many types of non-local models that exist within the groundwater community is that some of the parameters are really hard to figure out what to do with. We use them as fitting parameters most of the time, but like, how do we how do we get data to help inform on those? I find really hard. Some of you might be a lot smarter than me and might have ways of figuring that out. But what I like about that sort of dual domain model that's used within streams, that includes the connected stream and the less connected hypereic zone and eddies, and that sort of dual domain, mobile immobile domain in aquifers, is that I can conceptually understand what the storage zone looks like and the idea of exchange between them. I have trouble with some of these like fractional derivatives. I don't know what dc to the 1.3 dx to the 1.3 really means. Like I conceptually struggle with that a little bit more. So I do think the equations are quite similar, but the ways of describing them. Someone like Rena Schumer, for instance, would be a great example of someone who has taken these non-local models and applied them across a variety of systems. So it would be interesting to talk with someone like her who's applied basically the same mathematics to stream systems, aquifer systems, geomorphological contexts, right? And so to me, as someone who's not a mathematician, I still think of them as being quite similar, that the jury is out in terms of what the right equation is to describe these systems.
Thank you, Kamini. I think the next question seems also kind of related to groundwater. Now you mentioned groundwater community. This may be outside the scope of this talk. Are pumping tests an option to map out subsurface connectivity when ER and tracer tests aren't used?
Yeah, pumping tests are a little hard, right? Because the problem with the pump test is that you just get a single value of K. You get this sort of composite average it's unclear what the support volume is. You just get this single estimate of K. Now, you might be able to use things like hydraulic tomography, which is like the world's fanciest pump test, right? Where you have multiple pumps in different wells to sort of get at heterogeneity of K. But I think connectivity, part of the reason all of us struggle with it is because it's just so hard to measure. Like we're so data limited, and geophysics isn't, necessarily going to solve that problem for us because of resolution limitations, but at least it gives us some idea of connection, which is such an important characteristic in hydrogeology for so many reasons, or in hydrology for so many reasons. So yeah, I think the pump test would be a hard one, just because we just get this single block number that would be hard to do much with.
Okay, there are a lot more questions. Ellen, what do you, or Kamini, we can continue answer the question if you prefer, or depends on how you would like to go on. There's like 11 new questions.
I'm happy to take.
Yeah,
my gosh, there's
we'll
so
go.
I'd
Yeah.
say
I'm happy to take a few more if there's.
Yeah, we
more.
still got over 100 people attending, so if Kamini is available, let's go for a few more questions.
Yeah, I blocked out a little time after this. So.
Sure. Yeah. Next question is about ferrocrete that you were talking about. What is it exactly? Does it extend from the stream bed down to some depths at a constant density, or is a densest part is a density part at depth? It seems like the layer is modeled or assumed would make a large difference in the hyperea zone response.
Yeah, absolutely. So in fairness to you, I had never seen a ferrocrete until this system myself. So it's basically pebbles cemented by iron oxyhydroxides. And for those to precipitate out, we need oxygenated and low oxic water to mix. And so we see it at sort of the interface of that hypereic bounds, probably because of that reason. So we're seeing oxic stream water mixing with low oxic groundwater. So we are seeing it with depth primarily, probably at the interface where the sort of hypereic exchange has always been. And so what's probably changed is just the metal loading within that system. But those things are old. Like those ferrocretes are really old, pre-mining, I think, from when they've been dated by other people. So those features have been there for a very long time. But I'm pretty sure it's that mixing of water that allows those ions to precipitate out of solution and make that ferrocrete layer.
Okay, cool. Next one is about your tracer test. Are there ecological concerns permitting requirements for inputting salt tracers into streams?
Yeah. So if anyone out there is working on ecologically sensitive systems and are running tracer tests, I have a spreadsheet that I use to try to figure out how much salt we can put in. So it's a little complicated, right? So it depends on the system, but we often have to go through a permitting process depending on where we're working. And one of the things we think about is the loading of salts. So can we keep the concentrations low for ecologically sensitive areas? In some ways, it's actually easier for the geophysics to deal with low concentrations of saline anyway. We have all kinds of struggles when we have small, focused targets that have really high contrast and conductivity. It's really hard because of the way that we do inversion to capture that shape anyway. So having diffuse low concentration targets is actually a little easier for us to see within complications of noise anyway. And so we try to keep concentrations low. If you calculate mass, however, that can be an issue, because even low concentrations for 48 hours add up potentially to a lot of mass. And Ellen can certainly comment that you can carry a lot of 50-pound, sorry, I don't know in kilograms, bags of salt into the field to do these sorts of tracer tests. So yeah, we do have to go through a permitting process. We have different levels of concentrations that we think about, and many of these systems for like sodium chloride than for some of these other tracers. But yeah, we do try to be sensitive. Some of the systems that we work on are really sensitive and we have to use very low concentrations, but it seems to work pretty well with the geophysics still.
Great. So some questions about if the recording will be available. I just put a link there. All the talks from WR are available in that link, so feel free to go check out. It will be, the video will be uploaded within a couple of days of this talk. Okay, I'm moving on to the next question. Thanks for the great talk, Kamini. What about the hyperrhea zone in arid region, where the groundwater is very deep, sometimes more than 15 meters below ground surface? The surprising thing is that still in the drought period, some of the river is still flowing in some areas.
Yeah, that's a super interesting question. I haven't worked in a lot of those systems. So one of the complications probably in arid regions is sort of coming back to that karst question a little bit, in that if you have a losing stream where the flow path doesn't come back, you don't have a hyperrheic zone by definition, right? You just have losing stream flow paths. And so I imagine it's quite complicated in some of those systems, because you probably have these little small zones. There's a great paper by Kasahara and Wanzel, I think back in 1993, but I think that's who it was. It was a really cool image that actually drew all the little flow paths. This is also from the H.J. Andrews in Oregon, but they show all the little scales of exchange pathways between the surface water and the groundwater, and these little tiny short ones and these super long ones. And I would imagine that in arid regions, that might be even more interesting. The locality of your hyperrheic zone must be super interesting in systems where the groundwater table is potentially, if it's lower than the stream, you might just not have a lot of exchange. I don't know the answer to that. It feels like that might be a tough system to see much of a hyperrheic zone, just because of the fact that you would be losing most of your flow paths. So I don't know the answer, but it feels like that's a complicated system just because there might not be a ton of hyperrheic zone.
If I can just interrupt for a second, I would just direct everyone who's interested in this. There's a series of papers from the 90s by Nancy Grimm and Stuart Fisher. They're stream ecologists. So they were looking at hyperrheic exchange in ephemeral streams in connection with macroinvertebrates, but that's the only body I know on desert streams, particularly of research on hyperrheic.
That's very cool. Yeah, there's a lot of people working on sort of intermittent streams. I'm trying to think, like Margaret Shanafield at Flinders University in Australia does some work on hyperrheic exchange and intermittent streams. So there is a community that's working in those sort of arid environments. And so there must be some hyperrheic work in there. I'm just not as familiar with it. It feels like hard systems to me.
Okay, next question. I think it's probably from ecologist. Great talk. Have you made any observation on gas exchange like CO2, methane between the stream and hyperrheic zone?
I haven't. No, I'm so far afield from that I wouldn't even know where to start with that one, just because I'm so bad at that stuff. But I am sure that there are probably people that have been looking at gas exchange. Trying to think off the top of my head who to recommend to think about for that. I don't know if Jay Zarnetsky's still on here, but maybe someone like Jay has worked on some of those things. I don't know off the top of my head, but no, I have not done that work.
Jay is on the talk, but I think he probably can't unmute. Jay, if you add it to the chat, please.
he might know anyway.
Okay, I think it's getting to the end of the question. One is the last two. The first one is, great talk, Kamini. Any plans to return to Cement Creek to measure, hopefully, recovery in the years after the Gold King mine spill?
Yeah, this is certainly the very beginning of our work there. So it makes me always a little nervous to talk about new projects where we haven't spent a ton of time there. But one of the things that we really want to think about are sort of some of the geochemical characterization to look at those colloid associated metals and what those chemical associations might be. So we've been talking about going back. We have some new students starting in the fall, thinking about sort of, SEM, to maybe look at bonding info, X-ray photoelectron spectroscopy, maybe to look at surface characteristics of some of these things. So yeah, we're definitely hoping to go back and do a little bit more work with this. This is just the start of what I'm hoping will be a longer term project.
It would be great to see how much has happened in the years. What new remediation methods for contaminated stream do you participate developing from this approach?
Maybe I'm lying a little bit, and then I'm pretty far away from remediation actually at the end of the day. But what I think we can talk about from data like this is what might be effective. And so, it's hard to do sort of in-stream work if your stream isn't exchanging with groundwater and you've got metal laden groundwater coming into your system. And so I'm sort of a couple steps away from like the smart ways of remediating these systems. But to things that might make Ellen happy is there has been discussion in some of these landscapes about introducing beavers and introducing ways of sort of driving more hypereic exchange through either building features or having animals build features that sort of slow down waters and enhance hypereic exchange. So there has been some talk in these areas about doing these sorts of things. So in terms of natural attenuation, in terms of engineered remediation, I know less about that and can't say much smart to answer your question, unfortunately.
Okay, next question about ER. The capacity of ER sounds really helpful and interesting. Can you say more about if it is possible to use ER to detect changes in salinity in like nearshore wetlands, like when you have salinity gradients?
Yeah, so people have done some great work on salinity variability with electrical resistivity. The thing to keep in mind with these methods is that they're sensitive to more than salinity. So they're sensitive also to moisture and temperature, for example. And so if you are thinking about looking at something through time, making sure that you have some measure of what the changes in temperature are within your system and changes in moisture will help you in terms of correcting your data for those changes. It also helps to have hard measurements as opposed to sort of the soft measurements of geophysics on electrical conductivity so that you can make sure what you're seeing within your data makes sense with the sort of real measurements of electrical conductivity that you have. But certainly there's been quite a bit of work of people looking at wetlands or landfills or submarine groundwater discharge where these big contrasts in salinity with electrical resistivity. And some really neat work where people have even dragged resistivity behind like a kayak, for instance, where they float electrodes and GPS in where they go so that they can look at paths along streams or bigger boats. So those are maybe some things that might be of interest.
Okay, there's another question about dry river. In channel reaches that are dry or intermittent, when they resume flow from local groundwater, was the rate of rewetting of subsurface zone be different or matter? Thinking about how displacement of air from interstices might take longer in the later than in the former.
That's a super interesting question and comment. I would assume that is also true. As someone who doesn't work much on beta zone hydrology, I can't, or intermittent streams, I can't answer that question, but I would assume that you are correct in that. There is probably some literature out there on rewetting of stream beds. That's a super interesting question you brought up. I just don't know enough to say for sure.
Great, that's the end of questions. Thank you everyone for all these really interesting questions and being here. And I'm really excited to see you bring hydrophysics and geophysics and geochemistry together. So it'll be cool to see what happens in the next years. Alan, do you have something to add?
No, just thank everyone again for attending. Thank you, Kamini, for a really intriguing and obviously very stimulating seminar. And just, I'll be sending in an announcement around a week ahead of time, but just remind everyone that the next seminar is May 18th, and Michelle Koppes of University of British Columbia will be talking about braided rivers. So thank you again.
Thank you, everyone. Yep. Bye.